Thanks so much for the invite to come along, and I've got Hannah as well. So cool. I'll just get cracking, shall I? So today it's World Measurement Day. World Metrology. Metrology is the science of measurement. And I guess you've heard the word measurement, but I'd like to tell you a little bit about what it really, really is. So measurement is all about comparing something that you don't know against something that you do know. So, for example, you do know that the marks on the ruler are telling you what a centimetre or a millimetre is. But what you don't know is the size of the thing that you want to measure with it. So you do know the length of a ruler, but actually is about trust. You know, trust. You need to trust that the values marked onto the ruler are what they say they are. So if I've got this large chicken, here's my large chicken, and I think that's a big chicken, I want to measure its height. That's why I think it's a large chicken. That's the size of my car. I get my ruler and I put it up against the side of the chicken, and great, I can measure its height. The thing is that the ruler itself might be wiggling a bit. The chicken might be moving all over the place. So how you do the measurement will also affect the result. And we, the people that Hannah and I work with, the National Physical Laboratory, NPL, are all about trying to do that measurement as accurately as possible to get as good a result as we possibly can. Oh my goodness, the ruler's moving. Right. Now, I don't know if you saw this. There was an advert for this talk, and it had a teaspoon on it. And you might think, what's a teaspoon got to do with measurement? And the answer is loads, because we use teaspoons to measure medicine or sugar or milk or whatever it is that we're spooning out. And I went into my teaspoon drawer, and these are my teaspoons, and I've got, this is not all of them, I've got 27, all different. There are a couple that are the same, but 27 different, completely different teaspoons, and they were different in size. This smallest one here at the far left is about a seventh of the size of the largest one. It was just crazy. Now, I guess it doesn't matter if you're doing some cookery and you were using teaspoons to measure out quantities of things in your recipe. But if you were giving out medicine, that would be a problem. And the National Health Service, the NHS, discovered, they wrote a complaint that teaspoons could vary from 2.5 millilitres to 7.3 millilitres. That's an enormous difference. So one is 3 times bigger than the other, and that could make a big, big difference. Now, teaspoons, also spoons. There's a saying that says they were born with a silver spoon in their mouth. Now, that doesn't actually happen. It's just saying that they were born with lots of money and a nice big house, just because that's where somebody was born. They were privileged. So you have these very rich people, and then you have people who are not quite so rich. And I've represented that here with these two spoons. What happens when you have lots of people who haven't got much and a few people who have got a lot? You get a revolt, you get a war, you get a revolution. And this is what happened in England in the 1200s. King John had loads and loads of stuff, and all of the people said, you've got too much stuff and you think you're above the law. That's awful. We're going to get you to sign this thing that says, I agree that I'm going to rule by the laws as well as, because, you know, it's like saying the leaders can do whatever they like. So he signed this thing. And interestingly, in there's a thing that says that there's only going to be one way to measure stuff. So this is where I get quite excited because I'm a measurement scientist. It's talking about how you measure wine and ale and corn and cloth, and how you measure the weight of things like vegetables or fruit or anything. So this already is saying there's only one way to measure stuff so that it's fair. When you measure stuff, you know that you're being fair about things, which I think is very, very important. I like truth and being fair. So this is, again, why I like measurement. Now, this guy, Henry I, the king, he measured the distance between the end of his nose and the end of his thumb when his hand was outstretched. And then that distance was described as the yard, which is a bit like the meter. It was a way of measuring length. And you might think, what a ridiculous thing to do. Why would you do that? It's not as silly as it sounds, because if you're measuring cloth, you'd hold a piece of cloth, and it would be very easy to measure the width of a piece of cloth by between your nose and the end of your outstretched hand where you're holding the cloth. So it's based on measuring cloth. So this is like the king's yard of cloth, and they've got a piece of metal and they put 2 scratches on it and they said, this is the yard and we're going to use it from now on. Now, This then became an international idea, and the French set up this international system of units, and this is the home of measurement. It's in Paris. These are some people a couple of years ago, so it's still there today. And in this lovely building they set up, it's a bit like the King's Yard, except these were things that would be used all over the world, not just in England, not just in France, but everywhere. So they had the kilogram, which was a piece of metal that weighed exactly a kilogram. It was the kilogram. And the meter, which was a piece of metal with 2 scratches on it, and the distance between those 2 scratches is the meter, and everything is compared against that. So if you had a school ruler, then that school ruler would have been compared against something which would be compared against the meter, which is kept in this building. So this is international. Everybody is using it. So that's really, really useful if you want to sell things to different countries. So that's why today is National Measurement Day. The 20th of May, 1875 was the year that thing was signed, that the whole world would agree to use the meter for measuring length and its related centimeters and millimeters. So they've got the meter. Yeah, we've got a candle for the meter. And the kilogram, which of course we use to measure the mass of things, and the gram as well, which is related to it. So the kilogram and the meter were kind of used first in 1875, and then since then we haven't stayed still. We've created other units to measure other things. We've got the second for measuring time, and that's really well defined exactly what we mean by a second. Everybody uses the same second. We've got the Kelvin, which is used to measure temperature. I guess you've heard of degrees Celsius. That's what they use in weather reports. It's related to this special unit that we internationally use. Scientists and engineers use the Kelvin. The ampere, you might have heard of amps, amperes. That's how we measure electricity. Mole is something you use in chemistry. It's a real word used to work out how you combine chemicals in chemistry. And then, of course, there's the candela for telling us how bright light sources are. And that kind of makes sense, doesn't it? Because the word candle, it's 1 candle power. It's how bright a light is. So everything is just measured against these things. So the world is big. But if I wanted to make one of these, and I needed to get all the bits to make it from everywhere, these are just parts of a phone from all over the world, then the only way I could do it was if everybody was measuring the same way. Otherwise, bits would just not fit together. And it reminds me a bit of languages. If you were here, you'd say hello, or hi, or bonjour if you're in France, or how far if you're in Nigeria, or sanu, or hola, or privyet, or ni hao, or namaste. All of these different ways to say hello, but everybody is using the same kilogram and the same meter and the same of those other things to measure things. So it kind of all works, which is nice. It's an international system. So this is where Hannah and I work. Nice building near London, near Hampton Court. And we've got about 1,000 people working in there. We're owned and run by the UK government, the same as your school, really. So we're paid for by the government. We've got about 400 different labs in here, laboratories, where we can do all sorts of experiments. And I'm going to show you inside one of our labs. This is my favorite, I think, of all of the labs. So here's someone setting up an experiment, and you've got this incredible array of stuff on the walls here. This is all part of the experiment. You have to build the room in order to do the experiment. And it's just gigantic. This is probably about the size of your school hall. The picture makes it look smaller than it is. It's gigantic. Really exciting measurements going on in here about how powerful mobile phones are when they give out their signals and similar sorts of things. And you can't, where we work, we always have these funny stories. Here's a couple of odd things that I had to measure. I built a machine to measure how shiny a cat is. So we put these cats, we held them and stroked them and put them up against the side of the machine, and it came out with a number that said how shiny the cat is. Great, because somebody wanted to know how shiny cats are. And then we got this other thing. We got sent lots of biscuits and chocolate, and we had to measure for the biscuits how crisp they were. We wanted to see how the different types of wrapping kept them fresher for longer. And a way of working that out is to listen to the sound that they make when they snap, when you break them. So we built a biscuit staleness, crispiness measuring machine. So there are lots of different ways to measure things, and mass is really important, really very important. We use it to measure all sorts of things, and we use all sorts of machines to measure them. And we have this international system, and everybody uses the kilogram, which is about the same, which is what a litre of water weighs pretty much. That's where the definition of the kilogram comes from in the first place. And there's lots of different machines for measuring mass. You've got these sort of kitchen scales, we've got these balances. You've seen, you put something here and something else here, and then this thing here, a lorry drives onto this thing here, and there's some sensors underneath, and it gives a number. It's just like a larger version of this. So lots of different ways of measuring things, but they all measure the same thing, the kilogram. And in shops, I put here that solids, if you look on the side, they're labeled by mass, kilograms. Liquids, it says how many litres of things you've got. But ice cream is interesting. If you look on the side of the packaging of an ice cream, it describes its mass in kilograms and its volume in litres as well. So ice cream isn't quite sure whether it's a solid or a liquid. Now, this is Purdy, one of my friends at NPL, and she's built this machine here that really, really accurately measures how heavy things are, the mass of things with the kilograms. And this is world leading science. Purdy started work where we work when she was 16, and now she's about 22, I think, and she's still doing this amazing science here. Purdy's brilliant. I'm going to whiz through these things. I just want to show you that there's lots of different ways of measuring things. So if you had a book, you'd measure it with one of these. If you wanted to measure your height, you'd probably use a tape measure. If you wanted to measure a football pitch, you'd use one of these. And you can actually measure the distance between the Earth and the Moon using something like this. And using that device, we've discovered that the distance between the Earth and the Moon is changing. The Moon is actually moving further away from us by about 4 centimeters every year. So come back in several million years and it will really be a lot further away. So we can measure that accurately, which I think is absolutely fantastic. I'm not going to show you these slides. Oh, I'll show you this because it's fun. This is the world's smallest snowman. We made him. He's really tiny. You could fit 5 of these on the width of a human hair. This is just an example of the crazy science that we can do. We can make really, really tiny things. And you can only do these things if you can measure things really accurately, which is kind of the excitement of it all. I want to tell you a little bit about clocks. This is NPL's time team, or some of them. There's about 30 people making really, really accurate clocks where we work. And this is the inside of part of one of their clocks. And I don't know if you know about atoms, but there are things that are smaller than atoms called ions, and they're held, just one of them, inside this tiny thing here, and they ping it, they ring it like a bell. And that pinging sound effectively is used to give us a time signal, and that's what the newest versions of the second are based on, pinging individual atoms, which I think is absolutely amazing. So thank you, these lovely people here, for making these really accurate clocks. And without these clocks, lots of stuff would not work. So, you know, sat nav, telling us navigation stuff, telling us where we are in the mobile phones, that all relies on really accurate clocks like these to tell us where we are. I thought I'd tell you a little bit about the candida because this is the thing that I worked on. It's how bright light sources are. And I just thought I'd show you this, which is just crazy. If I wanted to measure the lightness of these things, I'd get a special machine, I'd measure it, I'll strap it on there. And the machine would actually measure that this area here is the same as that area there. Does that look the same to you? Does B look the same as A? Hey, don't to me. Let's just move this here, that this is the same as this, and this is the same as this. So these are actually exactly the same, which is really, really weird. It just makes no sense to me, and yet they don't look the same. And this is because we see things in a different way to the way that machines measure things. And in the future, we want robots to see things the way that people see things. This is actually happening right now in things on mobile phones, for example, facial recognition stuff. training machines to see things the way that we do. So again, these look different to you, and yet when I do that, you can see that they are actually identical. It's really, really weird. What's happening is that this is surrounded by dark things, so it looks lighter than it really is, and this is surrounded by light things, so it looks darker than it really is. And there are other effects too that are coming into this, so it's really weird. So training machines to see the world that we do is another type of measurement, and really, really useful. Right, so there is just one system of units that's used all over the world. There's the kilogram, there's the meter, there's the second, and there are these other ones: electricity, temperature, amount of substance, and light. And if we wanted to make or enjoy ice cream, we would use all of these units. We'd use a kilogram to measure how much stuff we've got. When we're making the recipe, we need to measure the size of the containers, which we'd use the meter with. We've got the second, which is to tell us how long to cook it for. When I say cook, I mean freeze. We use electricity to freeze the ice cream. So there's current measurement involved in this. You need to measure the temperature that you're storing it at to freezing it to, and you need to know how many ingredients you've got, and you need light to read the label. So just the sheer act of making and enjoying ice cream uses all of these different types of measurements. So that's why Hannah and I work at this place looking after measurement for you, for the world, to make it all happen. I'd like to ask you what you think a scientist looks like. I showed you photographs of some. That's Purdy. She helped make the kilogram. And then these people here work on the clocks at NPL. Now, what do you do when you want to find something out? I go to Google. So I went to Google and I typed in scientist for the images, and this is what came up. And there's lots of people there. They're all wearing white lab coats. I think if I asked you to do a drawing of a scientist, you might well draw this. Actually, you know what? I'll change the setting. I'll change it to cartoon. Let's have a look. Set the setting to cartoon. This is maybe really what you might think a scientist looks like. Crazy man, white lab coat, chemistry. We don't look like this. We really don't. Hannah and I do not look like this. Well, maybe I look a little bit like this. So let's go and look. We're going to go for a little lab tour now. Now, in normal times, I wouldn't be here on your screen at school. You would come and visit us, and we take you on a little lab tour, and we go into some labs, some laboratories, and see some real scientists talking about their science and showing them the amazing machines that they've got for doing the science that they do. And that's what we're going to do now. Because you can't be there, we video recorded it for you. So I'm now going to show you a little video. It takes about 7 minutes of looking around some laboratories and people telling you about the work that they do. They're actually involved in making machines that are used in hospitals to treat an illness called cancer. Cancer has these little cells that grow inside you. It's horrible, but by shining really bright light beams that are invisible into your body, just like at a dentist where they use x-rays, you can kill this disease, and it's brilliant. When I was your age, many more people died of this illness than do today because of these amazing machines that they've built. Anyway, let's go on a lab tour. Okay, here we go.
Radiotherapy is a treatment for cancer used within hospitals today. It uses beams of high energy but invisible light to kill diseased cancer cells within the body. Getting the power level right is really important, not too low and not too high. The science that measures this power is called dosimetry, and my team helps with these measurements.
Hello, my name is Frankie, and I'm here to show you the 3D printing lab at NPL. Here, we can make any object you want from just plastic. I will show you how the 3D printer works, and then I will show you what I'm making. With this printer, the surface the object sits on, which we call the base, is dipped into liquid plastic. A laser draws the shape of the first layer onto the base. This makes the plastic harden into a solid. The base then lifts out of the pool of plastic so that extra liquid drips off and is dipped in again to add the next layer. Prints take a really long time, usually a whole day. When it has finished printing all the layers, I remove the parts from the base and wash it in a special chemical to remove any liquid plastic. Then I cook it in a special type of light called ultraviolet light. Next, we have to cut off all the special support structure. The reason why we need this support structure is because otherwise the print will turn into a big floofy mess. After that, I sand it until it's smooth and then polish it. And glue all the pieces together. So here's my finished project. This is a phantom. The word phantom has a scientific meaning. It is an object which is exactly the same size and shape as a human body part, except it's made of plastic. But why am I making these plastic models? My colleague Warder will explain.
So here's Warder. She's a research scientist. And this is a 3D printed model of the bones around your hips. And Warder's pointing to some liquid containers that are also involved when she takes photographs. This is her special camera. It's a bit like an X-ray machine that you might have a photograph taken when you go to the dentist or a hospital. And here she is looking at the results. The important thing here is that they're three-dimensional images, so she can get all sorts of incredible information. This is Mohammed. Now, Mohammed uses software that's a bit like gaming software. It's a simulator of a real machine, so he can practice to see how he can adjust the controls of the machine to get exactly the right dose. Now, what we're doing is we're shining a really bright light beam. It's actually invisible light, but it's really powerful, into the body that kills cells that are dangerous to us, bad cells inside us. And you can see here that the power is concentrated in the red area, and he's adjusting the controls to make sure that just that tricky part of the body is being dosed with exactly the right amount. And you can adjust all sorts of things to make sure that that happens. Thanks, Mohammed. Now we're going to meet Hannah, and she's a materials scientist. So she decides what sort of materials are used to make these 3D models, these phantoms, as they're called. Here's the one that Frankie had earlier, and we've got a chest here that Mohammed showed, and we also got a head and Warder's pelvic bits there. The important thing for Hannah is to make sure that the material works exactly the same way that human bodies do. Now, I guess you know in light that you can have light that's absorbed, transmitted or reflected. It's exactly the same with this invisible light called X-rays. And we have a special detector here that measures how much is transmitted by different parts of the body. So here's Hannah's phantom, which is literally a 3D printed model of a human being, and she wants it to behave exactly the same way when you're doing a measurement as a human. So here's a detector, the X-rays, and hopefully it works exactly the same way. And by doing this, we generate lots of useful information that scientists can talk about. The last person we're going to is Ileana.
Hello, I am Ileana, and I am a research scientist working on medical radiation dosimetry here at NPL.
So this is Ileana's laboratory. In there, she's got this amazing machine, and hospitals all over the country have got these machines. They are combinations of cameras and sort of fancy X-ray machines, and the patient would normally lie on a bench. Here we've got a model of the chest of the patient. It's the same one that we saw with Mohammed earlier on. This is the real thing though, a real piece of plastic pretending to be a human being, and it's really important to line the whole thing up really properly. So Ileana and her colleague Alex are adjusting it to get the light beams in exactly the right place. There are markings on the side. Can you see? Ileana's pointing at it. So they've got to make sure it's in exactly the right place, and when it's running, you can see You can see the head moving across like that. Amazing. Now, when you have your photograph taken at the dentist normally isn't in the room with you. And here's Alex now in the control room, and he's adjusting the controls and making sure that it's all working properly, and you can see through here. Okay, back to you, Ileana, for the last few words of your lab tour.
All this work is very important and give patients, radiographers, physicists and doctors the confidence that the treatments benefit the patients. Remember, it is all about measuring the right dose, exactly the same way medicines need to have the right amount of active ingredient, not too little and not too much.
Well, thank you so much for coming for a trip around NPL with us. We looked, I think, in 6 laboratories and we saw all sorts of stuff. Right, I'm going to stop sharing my screen now, and I'm hoping that Hannah's there and we can take questions. Hello, Hannah. So this was scheduled to end about now, but I think we can hang around until you all get bored and go home or switch off, or somebody else switches us off. So if you'd like to pop some questions in the chat now, yeah, we can answer them. I think the main thing I wanted to say is that measurement makes the world a better place, and there's no better way to give an example of this than Hannah's work, which just brings medicine into, it makes the future now. I just look at stuff like Star Trek and TV sci-fi programs, and I just think, Hannah, you're making it all happen now. It's just amazing. and when I was the age that you young people are, many more people died of horrible diseases than die now, and it's all down to just improving medicine. It's just amazing. So if anyone wants to put questions in the chat.
There is a question. Derek Wood Junior School want to know that will the moving away from us have an impact on us?
The moon moving away from us. Yes, it's scary that, you know, that's happening. No is the straight answer, because it's a 250,000 miles away, and we're just talking about a tiny difference. The amazing thing is that I think we can measure it that accurately, and that we can see this tiny change. Yes, eventually moving away will cause big problems. Tides won't happen, the seasons might not run the same way that we do, and the moon is part of a mopping up system that draws asteroids and things away from the Earth. So in the long term, it could be a disaster. I think the moon is a major reason why there is life on Earth. But, you know, we are talking about several billion years. I mean, I'm talking billions of years before any of this happens. And we've only had life on Earth for about 4 billion years, and humans for a tiny proportion. So it won't affect us in the slightest. No.
Okay. So we've got lots of questions coming in.
Brilliant.
So St James Year 6, when did they first discover that they could use radiation to treat cancer?
Go on, Han.
Oof, that's a good question, James. I think it was probably about 100 years ago, but don't quote me on that. It's a while ago now. So yes, it's something that we're discovering using radiation all the time for different treatments. So, for example, I work in proton therapy. We've only realised we could use that within the last, say, 50 years, for example. But it's been around quite a while now, and we're getting really a lot of expertise in how to use it and use it to treat patients with cancer.
And it's changing all the time, isn't it? You're working on stuff that has never been done before, with the hope, expectation almost that there'll be solutions to illnesses that have never been done before, which is just something. Obviously, the vaccine at the moment is the big thing, but you're working on new things, which is really exciting. Loads of questions. Oh my goodness, 64 questions.
Catfield Primary School want to know, and it's Ellie, and it's related to another question on who or what inspired you to be a scientist. And another school asked, when did you know you wanted to be scientists?
Go on, Hannah.
Okay, I'll go quickly. I think for me, why I wanted to be a scientist was because it's all about solving problems. I used to play a lot of games on my Nintendo at that time. Problem-solving games, detective games. I always liked Sherlock Holmes and things like that. And science is being a detective. It's being a creative detective, coming up with new ideas and new ways to solve problems. So that's why I enjoyed doing science and why I decided to do science.
My dad was a science teacher. He brought home all the science demo stuff every weekend. I played with it. I thought it was just games. I thought it was fun. I didn't realize he was practicing the next week's lessons. So in a funny way, he kind of inspired me, but I didn't take science seriously. I thought it was just the fun thing that I did with my dad at weekends. So I was seriously an artist for quite a while, and then I changed my mind halfway through my A-levels. And what actually inspired me was someone at church who just said, come on, if you want to help humanity, if you want to help people, science is a better thing to be getting into than doing paintings. So I changed my mind. I moved from science to art. So up from art to science. I have to say, both are enormously creative. You start with nothing but an idea, you research, you find out what other people have done, you are inspired to do something, you end up with something that is not what you expected, but it does make the world a better place, and you can be enormously proud of it. And I'm talking about both science and art in the same way there, but I think yeah, science kind of helps people more. Everything around you is as a result of good science. Go on, more questions.
Okay, what happens if you shine the light that you can't see for too long? Is there a problem?
It will probably depend on the energy of your light, but yeah, we tend to make sure that we have strict rules on how long and how much we shine our lights for, especially for treating cancer. So yes, there would be a problem, but we make sure that there isn't by doing lots of rules and making sure the machine runs properly.
It's about killing cells, isn't it?
Exactly.
And by making sure that the light beam is in the right place,
yeah,
and the right power, ideally you just kill the cancer cells and not the healthy cells that are around it. So by adjusting, like in Mohammed's software, all of these things, you make sure that it's just right. Yeah, the direct answer is that you'd kill the healthy cells if you got it wrong. But it's all about getting it right, isn't it?
Lovely. One group of children want to know what the plastic is inside the machine, and another wants to know what the special liquid is that you use inside the Phantom, and how much do you need to use?
Go on, Hannah.
Okay, so different Phantoms are made of different materials. So we tend to use things called epoxy resins, which actually is quite a gloopy material that it sets when you add something called a hardener to it. And we add different powders in to make sure that it's the composition that we want, that it mimics the human tissues. So they're specially made, manufactured plastics that we mold into the shapes of our Phantoms. The question about the liquid inside I think you're talking about the pelvis Phantom. Yeah. So that's called a marker. So that is a liquid that has radioactive properties. So it's like I don't know how best to explain radioactivity. And
it's kind of glowing, isn't it? It's glowing. It's giving.
Yeah, it's like, a glowing liquid which we can then use our machine to look at, and it picks up that glowing power of the marker.
It's invisible glowing, just to make it slightly more confusing, isn't it? It's giving out light that you can't see, but it is glowing. Yeah, okay.
Two questions that come from Ninfield. The first one is Daisy wants to know what's an atom, and Etta wants to know, did you make any machines during COVID to help people?
Can I answer this?
Yeah.
Atom. Okay, so think of Lego. And when you make a Lego model, you've got the final model, but you've also got the little bricks that make up the model. And atoms are like the Lego bricks of the universe. They are tiny, tiny things which join together to make larger things that make large, and then you get bigger and bigger. Then you get people and pens and pencils and TV screens and iPads. There are billions and billions of atoms because they are so tiny, but they're just like tiny little bricks that everything is made out of. And there are only about 130. Is it? How many different types are there? I think it's about 130-ish, something like that, maybe 140 different types of atom. You might have heard of hydrogen and helium and iron and gold and silver. These are different types of atom, but there are only about 130 or so of them. Whereas think about how many different types of Lego brick there are. That's amazing. So atoms are the Lego bricks, if you like, that the universe is made out of. What was the other bit of the question?
What have you done during COVID time? What machines
COVID
did you do?
So yeah, we carried on making sure that the clocks are working. So we've got these most accurate clocks. The world relies on time being measured properly. So we kept the clocks going. A lot of us were all sent home. I think, Hannah, you're still working from home, aren't you? I am.
Yeah, I mean, I'm in the NPL today, but yeah.
Oh, you are? Right. Okay.
I'm there today doing some measurements on that big scanner that Warder showed.
So a surprising amount of normal work carried on, but also we were involved in designing ventilators for countries who don't have so much money as we have, so that they can build these things to help people breathe for only 100 or so pounds. They could build this thing from scratch. So we were designing new ventilators. We were also involved, a lot of us, in packing protective PPE, masks and stuff, into boxes. Hundreds of thousands of boxes of these things got put in. So we were doing our bit. We absolutely were doing our bit, and we carried on, not as normal. A lot of us were working from home, but we were doing our part for it.
Thank you. Unicorn Primary, again, 2 questions in one. Has radiotherapy been used successfully? How long does it take to make the machine? And the question, 3 questions. How do you get an iron into a clock? And it's
you do the first 2, and I'll talk about the ion into a clock. Go on.
Okay, so I think one of them, I think I might have forgotten the first question, but the second one was about how long it take to build the machine. So the machine that we have, the Elector machine, is made by Elector, a manufacturing company, and these machines probably take months to build. Because there's lots of really complicated parts and pieces that they have to put together, and they will go to the hospital or come to NPL, and they will build their machine, like the Linac, on site. This can take weeks as well, and then when it's been built, we do something called commissioning, which is making sure the machine works how we expect it to work. So it can be a long process. From first manufacture to actually then using it as a machine, you're looking at maybe like a year and things. It can take a while. The first question, I'm sorry, would you mind repeating that one?
The first question, I think we'll go on to the iron question.
Oh, all right, we'll do the iron question. So when we think about atoms, originally people thought atoms were the smallest things, but actually they're made up of even smaller things. And a bit of an atom is called an ion, and so I think they evaporate in the same way that water evaporates materials, and then they kind of get little tweezers effectively that pull out this tiny thing that's smaller than an atom. I mean, it's absolutely remarkably tiny, and they ride it about on waves, but not water waves, but waves of light, which are absolutely tiny. So literally they use these waves of light to carry and hold this individual tiny piece of material. I mean, we're talking about something that's 10 millionth of the size of a human hair. I mean, these things are absolutely enormously small.
We don't know the class, but it says, could the technology that you use be used to destroy the coronavirus?
It could probably, yeah. Whoa, I love it. Someone coming up with an idea. Yeah.
I think it's just trying to target that coronavirus because it's very small, and you
need to know where it was
to get it without damaging. We're saying we want to make sure we don't damage any healthy tissues and things like that. So targeting the coronavirus would be difficult, I think.
I think the coronavirus kind of goes everywhere in your body ish. concentrating in the nose maybe a bit more than everywhere else, but it does. Whereas with cancer cells, I think the useful thing is they sit in a clump, don't they? And you're pretty sure where they are. You've identified where they are, and you know where to zap with the beam. So sorry, you could kill it, but you'd have trouble finding them.
Okay, so
I'm liking the idea though, and coming up with ideas like that is what science is all about. So you are a scientist. Well done, whoever asked that question.
So Emily from Dublin, sent by Mr. Cross, is how dangerous is radiation to humans?
It's not dangerous if it's used properly, I would say. So as we say, we make sure we don't give too much or too little. We target our tumour. We make sure to spare healthy tissue and not target healthy tissue. And we use it to focus on the tumour to kill the tumour. If you took the radiation over the whole body and a whole person, that wouldn't be so good for the person. That wouldn't be very safe, but we make sure that when we do deliver radiation, we do it properly and accurately so that it's a safe treatment.
It's natural. Radiation is around us all the time. It's coming from the sun, it's coming from exploding stars, it's coming from the planet below us, from the Earth. It's absolutely natural, and there is a normal level. But if that level is a lot higher than normal, then we can be a bit sort of, it can make us ill. And it's all about, and because it's invisible, it's really tricky to know how much is actually there. And that's where the whole measurement thing comes into it. Knowledge is power. Knowing how much radiation there is really, really important.
Last question, because we've got to 10 o'clock. Inglehurst Junior School. As a scientist, what's the one thing you would really like to discover?
Oh, that's a very good question. A perfect question to end. Oh my goodness. Oh, Andrew, I'm going to put you first so I have time to think.
Time travel. It's no
Yeah.
coincidence that behind me I've got the TARDIS. I think time travel would be such a laugh. I'd love to go back and see dinosaurs. I have been involved in writing a book on time travel. I'm not trying to sell my book, I'm just saying. I think it would just be so amazing to see how wrong we are about stuff. I think dinosaurs will look very different to what we expect. I think history, if you go back and get the feel of actually being in places, I think you'll be surprised about how similar people were. We think about people not being clever or sophisticated, who lived in the 18th century or whatever. I'm sure they were just as ingenious and clever as we are today, if not more. And also, I'd love to see what happens in the future. I really, really would. But that's part of the excitement of doing science. We are part of making the future, and we are seeing stuff that is just amazing. It's like having a sneak peek at things that are going to come into the shops years in advance, which is quite good. So a time machine, but I don't think it's ever going to happen. Hannah, what would you?
To go on for that, I think like a teleportation device, so I can sort of hop from my bed to work or to a planet somewhere else. There's that ability to travel wherever, or flight. I know, well, to be honest, that's kind of being developed already. I've seen people on like devices and like drones and such to fly. But yeah, flight would be really, really cool, like an Iron Man kind of suit.
Thank you both very much. That has been amazing. The number of questions has gone to almost, well, more than 150 now. And I've said to the children that we will try and answer all of them.
Right, fine. Thank you very much. That sounds busy for the rest of the day, but okay, we'd love to do as much as we can. Thank you. It's been lovely having you. Or are you having us? Whatever. And meeting all you lovely people. I'm sorry I can't be there in person, but it's been great fun, and thank you, and fantastic questions. You're well done. You are the scientists tomorrow, I hope. So well done. Thanks for having us.